Let's now see the first algorithm which is used to guess this dynamic timeout timer in TCP, that is basic algorithm. Basic algorithm. So how does this basic algorithm work is, whenever you send the packet for the first time, so assume that we are sending the packet for the first time here. We are sending a packet, that is the segment. Then initially TCP doesn't know how long to wait, right? So it cannot guess it. So it can be, we don't know. It is the first time I'm sending a packet to the server and I don't know where this server is. Therefore, how long should I wait for the acknowledgement? I don't know. Therefore, initially we are going to guess initial round trip time. It is a guess. So it assumes that initial round trip time is 10 milliseconds, which is purely a guess. So I'm guessing that if I send a packet now, I might get the acknowledgement back in 10 milliseconds, and depending on that, I'll set my timeout to be 2 into round trip time, which is 20 milliseconds. So depending on that, I'll set my timeout timer as 20 milliseconds. So what does it mean? I'm sending the packet and I'm expecting the acknowledgement to come back within 20 milliseconds, right? So if it doesn't come back in 20 milliseconds, then I have to do something. So, but then luckily, assume that the packet came back in, I'm just taking a case, the packet came back in 15 milliseconds. 15 milliseconds. So what does that mean? You expected that it will come back in 10 milliseconds, but actual round trip time, ARTT means actual round trip time, IRTT means your initial guess, that you guess that it will come back in 10 milliseconds, but then it came back in 15 milliseconds. What does it mean? It is taking longer than expected, but since you are allowing it more time, like 20 milliseconds, you are lucky that you got it within the timeout. Then what should be the, whenever, so this, if this is the case, then when you are sending the next packet, what should be the timeout timer? For that, you have two options. Either you stick on to your initial round trip time, which means 10 milliseconds, and you stick to that, or you change it to 15 milliseconds because the last one has taken 15. So if you stick on to this 10 milliseconds, then it is nothing but static timeout timer. You are just simply fixing on to one value, which is static. Or if you increase the timer, or if you set the timeout timer to be whatever we got from this, which means if we got 15 milliseconds acknowledgement, therefore if you set it to be 30 milliseconds timeout timer, then you are very dynamic. So if you use the initial assumption and if you stick on to 20 milliseconds, you are very static. If you take the actual incoming packet and if you set it to 30 milliseconds, you are very dynamic. Both are dangerous. You cannot be very static. The reason is traffic will change, and you cannot be very dynamic, which means you cannot just depend on one previous packet and set the timeout timer for the next one. What happens is the last packet might have taken the longest path, or it might have taken the shortest path. If it would have taken the longest path, you overestimate the next time. If it has taken the smaller path, you underestimate the next time. I have a doubt here. So the safest bet is go for the biggest timeout timer, isn't it? Don't go for smaller ones, go for the biggest. Why can't you go for 100 millisecond every time? It is going to work either if there is traffic or if there is no traffic, isn't it? If there is traffic, fine, I am waiting enough. If there is no traffic, fine, it works fine. If there is no traffic, what happens is the packet comes back early, then also it works well. Then why can't I go for a very big timeout timer which is going to solve all the problems? The reason is, if I go with this big timeout timer, then in case if the packet is really lost, I will not be able to retransmit it for a long time. It is unnecessarily a lot of time waste. Therefore, if the timeout timer is very long, then the lost packets will be retransmitted very late. So this entire time is waste of time. If the timeout timer is very short, then what happens is the acknowledgement might have got delayed, but then you are not waiting long enough to detect the acknowledgement, unnecessarily retransmissions, which means if timeout timer is too big, too large, then it is going to lead to unnecessary time waste. It is going to lead to time waste in case if the packet is lost, if the packet is lost or the segment is lost, right? So whenever, see, one more thing, I generally use the word segment and packet interchangeably, but packet is a general term and segment is the term that has to be used at transport layer. So whenever I say packet, you please depending on the layer at which we are working, you convert the name appropriately. Okay, and now if the timeout timer is too small, then what happens is unnecessary retransmissions will happen. Unnecessary retransmissions means you will not wait for good enough time. So you will send a packet, and then by the time acknowledgement comes back, you will again retransmit the same packet because acknowledgement is coming late. Therefore, too big timeout timer should not be used, too small timeout timer should not be used. We should choose them appropriately. So how am I going to choose it is, I'm not going to choose it as my initial guess, or I'm not going to purely depend on what acknowledgement came back. So I have to use a something in middle. So how am I going to use it is, initial round trip time, let us say, is 10 milliseconds, then timeout I have set is 20, but the packet came back in 15 milliseconds. Okay, actual round trip time happened to be 15 milliseconds. Now what I do is, I'll compute for the next packet what should be the round trip time we should expect, that is next RTT. Initial RTT is my guess, actual RTT is what has happened, and from these two numbers I am going to guess the RTT for the next packet. So NRTT is alpha into initial round trip time plus 1 minus alpha into actual round trip time. This is the formula I am going to use, where alpha is a smoothening factor. Alpha is smoothening factor. Smoothening factor means it is used to take the average, some kind of ratio. So in case if alpha is 1, then what happens? If alpha is 1, then next RTT is equal to initial RTT, which is nothing but purely static. What happens if alpha equal to 0? If alpha equal to 0, next RT equal to ARTT, which means whatever is the previous packet we got, we are going to always use the same that packet only as the next packet's timeout. Very dynamic. So it has to be, alpha has to be some value between 0 and 1. So this value will be given to you in the exam, whatever is the alpha, right? So for this calculations, let us assume that alpha equal to 0.5. Then using these two, if you substitute here, then I get that next RTT is going to be, I think, 12.5. So next RTT is guessed to be 12.5 milliseconds. So what does this mean? If the packet initially is expected to come back in 20 milliseconds, 10 milliseconds, but it came back in 15, then I am expecting that the next packet will come back in 12.5 milliseconds. So depending on that, I am going to calculate what is the timeout. So for the next packet, my initial guess is 12.5 milliseconds. So therefore, for the next packet, initial RTT becomes 12.5 milliseconds. From this initial RTT, I am going to compute the timeout. Therefore, timeout is going to be 2 into initial RTT. So what is that? 25 milliseconds. Therefore, while sending the next packet, we are going to set the timeout as 25 milliseconds and send the packet, right? And now let us say we got back, I have already written all these values so that computation will be easy for me. Now let us assume that we got back the acknowledgement now in 20 milliseconds. Did you observe this? Initially we expected that the packet will come back in 10 milliseconds, but it came back in 15, which means there has been more traffic than expected. Therefore, I am increasing my timeout timer. Next time I expected that the packet would come back in 12.5 milliseconds, but it came back in 20. Therefore, there is again a change in the traffic, which is actually increasing the traffic. Therefore, I had again increased it. So what happened is, actual round trip time happened to be how much? 20 milliseconds, right? Therefore, depending on these two values, I have to compute the NRTT. So NRTT value is alpha into IRTT plus 1 minus alpha into ARTT. So if I put these two values, then I get NR2T to be 16.25 milliseconds, right? Therefore, this is the next guess. For the next packet, we are guessing that the time, the RTT is going to be 16.25 milliseconds. So, for the next packet, IRTT will become, initial RTT will become 16.25 milliseconds. Therefore, for the next packet, timeout will become 2 into 16.25 milliseconds, which is nothing but 32.5 milliseconds. So, what is that we are doing next time is, whenever we send the next packet, we are going to wait for 32.5 milliseconds, right? So just look at this pattern. Initially we expected that the packet would come back in 10 milliseconds, therefore we are going to put it as 20 milliseconds, but the packet came back late, the acknowledgement came back late. That is why next time I increased it. Next time I am expecting that the acknowledgement will come back in 12.5 milliseconds, but it came back late. Therefore next time I increased it. The reason is the previous two acknowledgements have shown that there is an increase in the traffic. Therefore I am increasing the timeout timer, right? Now I am waiting for 32.5 milliseconds, expecting that it would come back in 16.25 milliseconds, right? Then let us assume that this time the packet came back in 10 milliseconds. Actual round trip time is 10 milliseconds. You are expecting that it would come back in 16.25 milliseconds, but as a surprise, it came back in 10 milliseconds itself, which means this time the traffic has decreased. Previously 15-20, now the traffic has decreased to 10 milliseconds. Then if you find out NRTT with alpha equal to 0.5, once they have given alpha, fix it. So with alpha equal to 0.5, if you find out NRTT, you will find it to be 13.125 milliseconds, right? Therefore, if NRTT is going to be 13.5 milliseconds, for the next packet, when you are sending the next packet, the initial RTT is going to be 13.125 milliseconds, and therefore timeout is going to be 2 into this. So timeout is going to be 2 into 13.125, so which is nothing but 26.25 milliseconds. Therefore for the next packet it is 26.25 is the timeout timer, right? So just observe this, how this this algorithm works is, initially we guess something and actually we get something. So depending on these two, we guess for the next packet what should be the initial RTT. Now this one becomes, this next RTT becomes initial RTT for the next one. Now this is the guess for the next packet, actually something happens. Now using these two, I guess for the next packet what is the NRTT, and now that one becomes the initial RTT. Now initial we have something, actually something happens. So using these two, I guess for the next one, right? And now this next one is going to be the initial for the next packet. So initially, if this is the case, then timeout is going to be double of that. So that is how this algorithm works. And the algorithm is dynamic in the sense, observe this, initially the acknowledgement came back in 15, but we expected in 10, therefore we increased it. And next we expected in 12.5, but it came back in 20, therefore we further increased it. But later we expected that the acknowledgement will come back in 16.25, but it came back very early, which means the traffic is showing a decrease. So we are also decreasing the timeout timer. So it is not just we are increasing the timeout timer, if the traffic decreases, we are even decreasing it, right? And even more, one more thing is, this entire algorithm, for example at this point when I am computing the NRTT, it is not just I am based on the previous packet's ARTT. The ARTT is a history, which means when I am talking about this timeout, I am taking into consideration this one as well as this one. All of them will come into consideration. The reason is when you use this in this formula, NRTT equal to alpha into IRTT plus 1 minus alpha into ARTT, this IRTT has been derived from the previous NRTT. And if you go back to that previous NRTT, that contains ARTT. So it is a bit confusing. Just remember that when I am working at the fourth packet, it means that I have already taken first packet, second packet, third packet into consideration, then only I derived this, right? Now that is how this one works. The disadvantage of this basic method is this is called basic algorithm. This is called basic algorithm. The disadvantage of this basic algorithm is always timeout is taken as 2 into RTT. So always here timeout is taken as 2 into RTT. And why 2? Why not any other number? This 2 has been used traditionally and everyone is using it, and there is no logic behind it. So just since there is no logic behind it, the scientist Jacobson, he has proposed a better method using which you will never use 2, you will use some other method. So this is the disadvantage of basic algorithm, using 2. Then Jacobson rectified it. So that is why we go for the next algorithm, which is Jacobson's algorithm. Okay.